Ah, cast iron. When you think about it, it feels like it's been around forever. We've all seen it from that heavy-duty skillet in the kitchen to the core of a classic car engine. It just screams durability. And these days, we love it for another reason. We think of it as being super eco-friendly. But is that the whole story? Let's dig in. So on the surface, the story for cast iron looks amazing, right? It's incredibly recyclable. The parts you make from it last for what seems like an eternity, so you're not constantly throwing things away. And it's basically the poster child for a circular economy, taking old scrap metal and giving it a brand new life. I mean, it seems like a total slam dunk for a green material. Well, you probably saw this coming. When engineers and scientists really started to crunch the numbers on the entire life cycle, the answer to that question, is it really that simple, was a big resounding nope. The reality is way more nuanced and, honestly, a whole lot more interesting. And here's the number that really throws a wrench in things. 3.3 million tons. That's the amount of CO2 equivalent emissions the German foundry industry alone pumps out every single year. That is a huge carbon footprint for an industry we all kind of assumed was green. So the big question is, where on earth is all that CO2 coming from? Okay, so let's put on our detective hats. To find the source of this massive, fiery footprint, we have to look at how cast iron is actually made. And it's a process that, you guessed it, involves incredible heat, some very precise chemistry, and a ton of energy. What you're looking at here is basically the entire recipe. It's called a life cycle assessment map, and it tracks every single thing that goes into making cast iron, from mining the raw materials to generating the power, all the way to the finished product. It's a really complex web, as you can see, but one part really jumps out. And here it is, the single biggest energy hog in the entire process: melting. Get this, over half, 52%, of all the energy used in a foundry goes into this one single step, just turning solid metal into a liquid. That, of course, takes a tremendous amount of power, and that's where a huge piece of the carbon footprint is born. Okay, so this brings us to the most surprising, kind of mind-bending part of this whole story. We all know recycling is good, right? So logically, if you use more recycled steel scrap instead of brand new pig iron, your emissions should just go down, 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 right? Well, maybe not. This is the common wisdom. It's what we're all taught. Making new pig iron is a major source of CO2. Steel scrap, on the other hand, is already made. It just needs to be remelted. So the logic is super simple. Swap the dirty new stuff for the clean, recycled stuff, and your carbon footprint should just plummet. Makes perfect sense. But here's the catch. It's a chemical balancing act. See, pig iron has a very specific high-carbon recipe that's perfect for making cast iron. Recycled steel scrap, it's more of a mixed bag. So to get that final cast iron to have the right properties, you have to start adding other stuff back in, things like carbon and special alloys, to get the chemistry just right. And those additives, they have their own carbon footprint. Okay, now look at this chart. This is where it gets really fascinating. On the left, we start with a standard mix using pig iron, almost 800 kilograms of CO2 per ton. Now look what happens when we switch to 25% steel scrap. A huge drop, down to 650 kilos. Awesome! But here's the paradox. When you push the scrap content even further to 40%, the emissions actually start to go back up. And hey, don't just take my word for it. The researchers who did this study summed it up perfectly themselves. Those extra materials you have to add in for higher scrap recipes, they eventually start to outweigh the benefit of not using pig iron in the first place. It turns out there's a sweet spot, and going past it is actually worse from a carbon perspective. Now, understanding this paradox doesn't mean we just throw our hands up and say recycling is bad. Of course not. It means we have to get smarter. This is an engineering challenge, plain and simple, and it has an engineering solution. The path to a truly greener iron isn't about slapping on a simple label. It's about precision. It's about optimization. And there's a clear game plan. It really boils down to 3 key steps. First, you have to look at your energy source. Second, you use high-tech controls to get incredibly precise. And third, you have to adopt a whole new way of thinking about the problem. So remember that melting step was the biggest energy user? Well, where you get that electricity from changes everything. I mean, it's night and day. An electric furnace that's running on power from a coal plant still has a massive footprint, but that exact same furnace, running on wind or solar power, the carbon footprint from its energy use basically drops to zero. And this is where the really cool modern tech comes into play. A modern foundry isn't just a big vat of molten metal. They use tools like thermal analysis where they can get a real-time exact reading of the iron's chemistry as it melts. This means they can add the perfect amount of alloys, using the perfect amount of energy, and waste absolutely nothing. It is precision manufacturing that leads directly to sustainability. So after going through all this, what's the big takeaway? It's that we have to move past these simple feel-good marketing labels. We have to develop a much more sophisticated, more grown-up understanding of what green actually means in the real world. The solution that researchers are pushing for is called a TEE assessment. Now, it sounds a little academic, but the idea is actually very straightforward. It stands for technical, economic, and environmental. It's a framework that forces you to balance all three things at once. You have to consider the technical needs of the final part, the economic costs, and the environmental impact. It treats sustainability as an engineering variable you have to solve for, not just a box you tick. And that really brings us to the heart of it. True sustainability isn't about finding one magical material or one simple action. It's the end result of a holistic calculation. It's a careful, deliberate balancing act between the materials we choose, the energy we use, and the performance we absolutely have to have. It just goes to show you, calling something green is easy, but actually engineering it to be truly sustainable, that's the real work. And it makes you wonder, doesn't it? If sustainability is a calculation, what other things do we just assume are good for the planet? What should we put under the microscope next?